Imagine the last normal second before control disappears. The headlights are on, the engine is running, and every tire still touches the road. On our gauge, the muddy water is only 12 inches deep, while the example car weighs roughly 3,300 pounds. Then the entire machine moves sideways, not forward, not under its own power, sideways as if the road has suddenly stopped holding it. The car does not need to float like a boat. The water only needs to steal enough tire grip for the current to win. That takeover happens through a chain reaction. Water pushes sideways, water lifts upward, the tires unload, and the body begins to turn. The terrifying part is not that floodwater looks violent. It is that dangerous water can look ordinary from the driver's seat. So where is the real limit? And how can a thin moving layer of water defeat a vehicle more than a ton in weight? Start with the number most drivers remember, 12 inches. The National Weather Service warns that 12 inches of rushing water can carry away most cars. Its flood guidance also warns that around 18 inches can carry away large vehicles, while 2 feet can carry away sport utility vehicles and trucks. But 12 inches is not a magic physical line. 11 inches is not automatically safe, and 13 inches is not the same situation everywhere. Depth matters, but so do water speed, vehicle shape, angle to the flow, road slope, tire condition, and what lies beneath the water. The water beside your door may be shallow, while the center of the crossing drops sharply, or while the current accelerates through a narrow channel. The warning exists for a reason. The National Weather Service says more than half of flood-related drownings happen after a vehicle is driven into hazardous water. Treat the official depths as reasons to stay out, never as targets to approach. The first force is drag, the horizontal shove of moving water against the vehicle. Water is not an empty visual effect. Every moving parcel has mass and momentum, and the car must redirect that flow around its body. Doors, wheels, bumpers, and the underbody interrupt the current. To the water, the side of the car starts behaving like a small dam. The faster the current moves, the more forcefully that momentum is transferred. Under similar conditions, doubling flow speed can roughly quadruple drag. This is why slow, deep water and fast, shallow water are not equivalent. A depth measurement alone cannot describe the threat. As the water rises, it also exposes more surface area to the current. More area gives the flow a larger target to push. Pressing the accelerator may feel like adding control, but engine power only reaches the road through tire traction. Without traction, more throttle adds noise, not authority. A car ahead making it through proves almost nothing. It may have followed a shallower line, met a slower pulse, or simply escaped before conditions changed. The second force is quieter, and it is the one drivers rarely feel coming: buoyancy. As water surrounds the lower body, the vehicle displaces it. That displaced water pushes upward against the car. The car's mass does not vanish, but part of its weight is now supported by water instead of the road. That means less normal force pressing the tires into the pavement, and the contact patches begin losing their mechanical advantage. Available friction depends on that tire load. Reduce the load, and a smaller sideways push may be enough to begin sliding the car. Now the trap becomes clear. The current grows stronger at the same time the tires become less capable of resisting it. Meanwhile, water can reach electrical systems, the air intake, or the exhaust path. A stalled car leaves the driver inside a problem that is still moving. Waiting for the body to visibly float misses the earlier danger. A vehicle can lose directional stability while its tires still appear firmly planted. The real threshold is not a painted line on the door. It is the instant resisting forces fall below destabilizing forces. On one side are drag and upward water force. On the other are tire friction, vehicle weight, and whatever geometry still keeps the body aligned. The water does not need to dominate forever. It only needs to win long enough to start the first movement. Engineering studies describe several failure modes: sliding across the road, beginning to float, or rotating and overturning under combined forces. The stability boundary is a curve, not a single depth. Faster water can destabilize a vehicle at a lower depth than slower water. Change the vehicle's mass, ground clearance, underbody, tire grip, or angle, and that boundary moves again. A driver looking through rain cannot calculate that curve. The required variables are moving, hidden, and changing faster than a safe decision can be made. Once the car slides even slightly, the geometry of the entire problem can change. If the front or rear loses grip first, the current can rotate the vehicle away from its original alignment. As the body turns broadside, far more surface area faces the current, so the sideways force can rise again. The first slide creates a larger push. The larger push creates more rotation, and the rotation can turn a small loss of grip into a rapid sweep downstream. The steering wheel may still turn, but a tire cannot steer the vehicle if the contact patch no longer has enough grip to generate force. That is why a vehicle caught in swiftly moving water can be swept away in seconds, even after the approach looked slow and manageable. Once the vehicle turns or stalls, rising water, current pressure, debris, and the road edge can remove options that existed only moments earlier. A larger vehicle feels safer because it is heavier and sits higher. Both facts can create dangerous confidence. Extra weight can increase resistance to sliding, and greater clearance can delay water reaching some components. But a taller, longer body also gives the current more area to push, while large enclosed volumes can create substantial buoyancy. Official guidance warns that 2 feet of rushing water can carry away sport utility vehicles and trucks. Ground clearance may postpone water reaching the cabin or intake, but it does not cancel drag, lift, rotation, or a missing road. The right conclusion is not that one vehicle class is safe. It is that every vehicle has a stability boundary the driver cannot see. Even perfect vehicle physics would not solve the most disturbing variable. The road beneath the water may no longer exist. Floodwater can hide a washed-out shoulder, a collapsed culvert, a sudden drop, or pavement weakened from below. A crossing that supported one vehicle minutes ago may erode further before the next vehicle reaches the same spot. The National Weather Service also warns that floodwater can conceal sharp debris, electrical wires, chemicals, and damaged road surfaces. Upstream rainfall, a blocked drain, or a failed obstruction can send a deeper and faster pulse into a crossing with little warning. Seeing the lane line through the water only tells you that light reached the paint. It tells you nothing about current speed or support beneath it. It may not even be raining where you are. Flash flooding can carry water from a storm that happened upstream or earlier. So what number should a driver actually use? For a flooded roadway, the useful driving threshold is 0 entry. Do not turn safety guidance into an experiment with your own vehicle. Stop with enough dry road to turn around calmly. Never drive around a barricade, and choose another route even if the delay feels inconvenient. Do not follow another driver into the water. Their vehicle, route, timing, and luck are not measurements you can reuse. A heavy car can be moved by shallow floodwater because drag rises, while buoyancy reduces tire load, until the current needs less force than the tires can resist. That is the hidden limit, not the moment the car floats, but the earlier moment the road can no longer keep it under control. Next, we will ask why a power line that can kill a person is usually harmless to the bird standing on it. Subscribe to find where normal stops.